Hello, I'm Past Paper Guy. I'm going to be solving the 2017 Paper 3 A-Level Physics paper from AQA. I'm going to be doing just section A in this video. As with all my other videos, then I would very strongly recommend you have a go at this one before you watch this video, and then you use it to help you understand the questions that you can't do. The mark scheme is quite a long and complicated one for this one, so it's quite a lot of people will find it difficult to understand. Our students found this paper quite challenging. Right, so here we are with question 1. As you can see, there's an awful lot of information about what's going on here before we even start the questions. So there's a lot to get your head around. Hopefully you've seen a microwave transmitter and receiver, and this image I think gives you the best idea of what's going on. You've got the transmitter here with a variable supply which is transmitting microwaves along here to this receiver. When you turn it on, then you can see that the signal strength at the receiver is at a peak, and then here when you move this metal screen further away from this line, then the signal strength drops, it says, to a minima. Right, I know it's on the next page, but I'm going to explain why this is the case. So we've obviously got an interference effect, and we've got destructive interference going on here. So we've got some waves which are travelling straight from the transmitter to the receiver, like so, and we've got other waves which are rebounding off there and onto there. Now the path difference between the direct wave here and the rebounded wave here, the reflected wave, the extra distance that that one has to go is going to be exactly 1/2 of a wavelength, which will cause destructive interference here. So the ammeter reading depends on the superposition of waves travelling directly and those reaching R after a reflection at M there. State the phase difference between the two sets of waves when it's at a minimum. So it's got to be pi radians. Sorry, I should use a pen. Pi radians, which is the same as 180 degrees. Explain why the minimum reading is non-zero when the distance x is measured. Okay, this could be a little bit tricky to start with, but the reason in the most simplest form is when the non-zero is because the amplitude of this one and the amplitude of this one is different. Why is that? Well, the ones that are going straight there will have a greater amplitude than the ones that have been spread out. They'll get lesser and lesser amplitudes as you go further and further out. So this reflected one has a smaller amplitude, smaller intensity therefore, than the one that goes straight there. Sorry, not the paper there. So the direct TR root waves will have a greater amplitude, so that's intensity, than the ones going TMR. Various reasons for that. You might lose microwaves on the metal plate, you'd have the strongest beam going straight ahead. They might reflect off in other directions as well. When M is moved further away, the reading increases to a maximum, then decreases to a minimum. So we're getting standard maximum minima due to 180 degrees pi radians, or 3 pi radians, or 5 pi radians, etc. The first minimum position student labels as N1, then records the value of X, next N2. Describe a procedure that the student could use to make sure that M is always parallel to the line marked before measuring each value. Okay, so there are various ways you can do this, but what you have to do is you have to measure the distance here and here at the shortest point and make sure that they're the same. The easiest way to do this is with a set square. So first of all, draw the line RT and then use a set square to measure 2 points on M, say the edges, and adjust them until both are equal. So it's a bit difficult to describe that, so it's much easier just to draw a diagram of this here. So there we have the T and R. Here we have M, and you put your set square in there, and you put another set square in there, and you measure that distance there and that distance there, call it x1 and x2, so e.g. x1 is equal to x2. Okay, so you put your set square on each end and you adjust M until these two values that you read off are identical. Okay, so this one is a graph exercise. It's not really too much based around the previous question. What it's more doing is working out if you know how to use error bars. So this is something that's pretty new this year, so there aren't many examples of questions like this. So we've got this expression here, which is representing this graph here, and we need to determine the maximum gradient and the minimum gradient from this. So to do this, what you need to do is get the paper, turn it round, get your pencil, and just work on trying to find the maximum and minimum gradient. So you start at the bottom of this one here, and you see if you can draw a very, very steep line. And the steepest line I can draw is going through the top of this one here, the top of the n equals 11 line. Because if I went any steeper, I'd drop off that one. Even though I'd go through this one, I wouldn't be going through that one anymore. So I can go through that point there. I can go through that point there. So there's my line. Now my minimum value I do for something very similar. So I'm going to start there and go through, right, so that's not going to work because that's not going to go through all of them. So I have to ignore that one. We'll start on this one, highest point of this one, and we can get through every single line there. Like so. Okay. Right, now there's a lot to do still. This is 3 marks. It takes you quite a while to do these questions. Just say you've got 70 minutes at the front of the paper to do this. The maximum gradient of the line is that one, G max, and that one's G min there. So we need some values, so best to use this point here, that point there, that point there, and that point there. Right, I make this just slightly higher than 1.2, that's 1.275 there, that's 1.28 there, so it's 1.277 about there. This one I make as 1.2 0.45, I think is closest there. I'm going to move this a little bit closer to me. Don't be shy to move your paper around when you're doing your work. This one here is about, that's 1.60. That therefore is 1.61. That's 1.62. So that's just a little bit less than that. So that's 1.67. Sorry, 1.617. So there, and then we've got G min here. This one here is pretty much halfway between there and there, so that's 1.575. It's worth taking a little bit of extra time in order to try and get these as good as you can. You could read them off from anywhere, but it's best to use as much of the graph paper as possible, and I think it's easy to read them when they're right at the edges, especially in this particular example. Right, so we now need to do, I'm just going to switch these two pieces of paper over. We now need to work out the actual values from this. So we've got G max is equal to delta y over delta x. So the change in y for G max is 1.617, take away, what's that line there, 1.245 divided by 14, take away 2. Wait, that's not 0 there, so just be careful. 14 take away 2. Now this is slightly different values to my trial run, so I'm going to have to work them all out. Divided by 14 take away 2 is 12. So that is 0.031. The units are meters. Right, G min next. Delta y over delta x. Right, we have 1.575 take away this one here, 1.277. Oh, hang on. I think I've gone slightly above that line there. So I'm actually going to redraw that one. Okay, so I think I made a bit of a mess of this, but luckily I did it in pencil, so I can rub it out and have another go. So there, so that is inside that one now. That's where I went wrong last time. I just missed the edge of that one. Okay, so that point there is exactly the same. This one, slightly different. Intercept, that's 1.275 there. Okay, much happy with that. So my previous one, I've gone outside the edge of that one. This one, I've gone inside the edge of that one. I'm just on the edge of that one, just on the edge of that one, and just on the edge of that one. Right, let's keep going. So that should be a 5 divided by 14 minus 2. Put that in the calculator, and let's see what we get. Oh, could have done that in my head. 0.025 meters. So these are both two. I'm going to do them to two significant figures. I don't think I could get really more than two significant figures. But I think they accept 2 or 3 significant figures for that one. So we now need to determine lambda using our results for G max and G min. So we need to go back to this equation here and rearrange it only slightly. This I want on the left hand side. So we've got square root of 4 blah 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 is equal to n lambda plus y. And I'm going to equate that to y is equal to mx plus c. So that equates to that. X, on the x-axis we're plotting n, so that equates to that. This is what we're plotting on this axis here, and so that must equate to that. So lambda is the gradient. So what we need to do is, we've got our maximum and minimum gradients, so we need to find the average of those in order to get the middle gradient. So lambda is equal to G max plus G min divided by 2. So that's 0.031 plus 0.025 divided by 2. Which is 0.028 meters. Okay, so lots to do there. You've got to be careful when drawing your lines. You've got to be careful when reading off the values, especially as these graphs have often got really horrible scales that they use just to try and put you off. Do your calculations. To find the gradient of the line in the middle, we just make an average of these two gradients, and that gives us our lambda there. Right, so we're continuing on now with 1 part 6. Determine percentage uncertainty for your results in lambda. So first of all, we need the uncertainty in lambda. So the uncertainty in lambda is the difference between the maximum and our average value. So the uncertainty in lambda is equal to G max take away our value of lambda. So that is equal to 0.031 take away 0.028, which is equal to 0.003. So the percentage uncertainty in lambda is going to equal our absolute uncertainty divided by our value of lambda, and we times by 100 to turn it into percentage. So 0.003 divided by 0.028 is that times by 10, nope, times by 100 even, gives us 10.714%. So I'm going to write 10.7% to 3SF. I think you'd write that to either 2SF or 3SF. The graph in figure 4 can be used to obtain a value for y. You are not required to determine the value for y. This is a truly horrible thing to ask, because if we go back to this, the value for y is the y-intercept here. So what we need to do is to extend this graph down here and just read off the value when n equals 2, when n equals 0. They started the graph when n equals 2, so we can't actually do that, which is very annoying. So we need another way, and the other way is to think about this line here, this line that goes through the middle of these, which had the gradient of this. Think about that line and then use mathematics to extend it back to when n equals 0. So we need to consider the best fit line, and that has a gradient equal to 0.028. We need a point on that best fit line. Well, the point, you could draw in that best fit line, but the point on that best fit line has got to pass through where these two join, because it's got to be halfway between these two, so it's always going to be halfway between these two, but where they join, halfway between them is on top of them. So the point that we can put in is where the maximum and minimum gradient lines cross over. So the point where G max and G min cross is on the line of best fit. Okay, so now we can use, we've got y is equal to mx plus c. So we can read off the square root of 4x squared plus y squared and n, where g max and g min cross. So we're reading off that value there and that value there-ish. You don't need to do it, so I'm not going to actually read off the correct values. Use the square root of 4x squared plus y squared is equal to lambda n plus c to find c, where that's from the graph, that's from the graph, and that is 0.028 meters from the previous question. Okay, so if we know a point, so that's our point there, we know the gradient, we can work out what the y-intercept is, and the y-intercept is this here to find c, and this intercept is equal to y in this term. It's a bit annoying that they've got y as well, but never mind. But there are lots of other ways you can actually solve this problem, so don't think this is the only way. This is the way that occurred to me. You could describe drawing in another best fit line in the middle, finding its gradient, and reading off a point to find its equation, and then solving it to get the y-intercept. And there are other methods, I think, as well. Right, next, 1.8. Suppose the data point here didn't exist. How would it change your values of these two, and therefore how would it change the values of these two as well? Okay. So G max is determined by this one and this one here. So if that point didn't exist, we would still get the exact same G max, because we can't make it get any steeper if that point doesn't exist. So that would not be affected. G min. At the moment, I've drawn that line there, but if that didn't exist, then I could continue to draw that line there, which means that that line would be of a lower gradient than that one there. So this would reduce. If that reduced, then the average of these two, that one stayed the same, that one has reduced, so the average of those two would also have to reduce. And if you think about the y-intercept over here, if I've gone from there to here, my line has got less steep, like that, that's pulled up the y-intercept, so that's going to increase. So that's going to increase there. Okay, so tough question, lots to do, but each individual part is not too difficult. I think this is the most challenging part.